Let's look at the algorithm for implementing a queue using two stacks. So here we have an empty queue with two stacks. We add items to our queue, let's say 10, 20, and 30. And we should also store these items in the first stack. So 10, 20, and 30. Now here's the problem. If you want to remove an item from our queue, that number has to be 10. But 10 is the last item in the first stack, so we don't have access to it. However, because we have a second stack, we can use this as an opportunity to reverse the first stack. So we pop each item from the first stack and add it to the second stack. 30, 20, and 10. Now our first stack is empty, and the second stack includes all the items in the order that should be removed. So now we can pop 10, and this will remove 10 from our queue. Beautiful. Next time we call the DQ method, we want to remove 20, and 20 is in the right position, so we can easily remove it from here, and this will disappear from our queue. Beautiful. What about adding new items? So if we add two more items here, 40 and 50, where should we add them? Well, if we add them here, this will mess up with the order of our items. Because next time we DQ, we should remove 30, and now 30 is at the bottom of our stack. So we should add 40 and 50 to our first stack. In other words, we use the first stack for adding new items or for the in-queue operation, and the second stack for the DQ operation. So now if we call the DQ method, we'll remove 30 from our second stack, and this will get out of our queue. Now, next time we want to call the DQ method, we are in the same situation as before. 40 is at the bottom of our stack. So once again, we should move all these items from the first stack to the second stack to reverse their order. So here's the algorithm. Whenever the second stack is empty, we need to move all the items in the first stack into the second stack. With that, let's go ahead and implement this queue. So I'm going to create a new class and call it queue with two stacks. Here we need two stacks, so private stack of integer. We call it stack 1. And another stack, which we call stack 2. Now let's implement the in-queue method. So public void in-queue. We always add new items to our first stack. So stack 1 dot push item. Now let's implement the DQ method. Public integer DQ. First, we should check to see if the second stack is empty. In other words, if we have some items here, we don't want to move the items from the first stack into the second stack because, as I explained earlier, they will mess up with the order of these items. So we'll move items from the first stack to the second one only if the second stack is empty. So if stack 2 is empty, here we can use the empty method or is empty. They're essentially the same. If the second stack is empty, then we're going to move all the items from the first stack into the second stack. So as long as the first stack is not empty, we keep popping items and pushing them into the second stack. So stack 2 dot push, and we give it stack 1 dot pop. Now these items are in the right order to get removed. So finally, we call stack 2 dot pop and return this value to the caller. Let's test our implementation up to this point. Back to the main class. I'm going to create a queue object. So we type queue WTS as a shortcut for queue with two stacks. We call it queue. Now let's add a few items here like 10, 20, and 30, and then remove the first item. So queue.dq. Let's print this on the terminal. So first, 10 got removed. Beautiful. Let's try it one more time. So queue.dq. This time we should get 20. Beautiful. And one last time. Now we should get 30. Now, what if we DQ an empty queue? Let's see what happens. We got an empty stack exception. This is not terribly bad, but it's better if you throw an exception like illegal state exception or queue empty exception. So back to our class, we want to check to see if both stacks are empty. If we don't have any items in either of these stacks, that means our queue is empty. So if stack 1 is empty and stack 2 is also empty, then we'll throw a new illegal state exception. Let's try it one more time. Now we got a more meaningful exception. That's better. Now here's a question for you. What are the runtime complexities of these operations when we use 2 stacks to implement a queue? Pause the video and think about it for a second. Here's the answer. Enqueue is an O of 1 operation because we simply add an item on top of our stack. But what about dequeue? Well, in the worst case scenario, we have to iterate over all the items in the first stack and move them to the second stack. So the cost of this operation increases linearly according to the size of our queue. So here we have an O of n operation. Now let's implement the isEmpty method. So public boolean isEmpty. We're going to use the same logic that we have used over here. So I'm going to extract this boolean expression, move it over here, and then reuse this method in our dequeue method. So if isEmpty, that makes our code cleaner, more readable, and we have reused this logic. So there is a single place that we need to change in the future if we have to. Now let's implement the peek method. That is very similar to what we have in the dequeue method, but instead of popping an item from the second stack, we should simply return it. So to save time, I'm going to select this code, duplicate it, then rename this to peek, and replace pop with peek. Now, if you notice, we have repeated these 3 lines in both these methods. This is a good opportunity for refactoring. So I've selected this code. On the top, we go to refactor, extract, method. We can call this move stack 1 to stack 2. That is exactly what we are doing over these few lines. So refactor, IntelliJ detected that we have 2 occurrences of the exact same code. So let's refactor all of them. And here's the end result.